A thin layer of dirt holds a secret that could rewrite human history. This is the story of the comet impact theory, a bold idea that says our planet was struck by a cosmic catastrophe 12,800 years ago. By the end of this journey, you will see how a single event from space might explain the sudden disappearance of entire cultures and the great beasts of the Ice Age. We will sift through microscopic diamonds found across continents and decode ancient stories written in stone and ice. What does it mean for our past if the sky once truly fell, the world was supposed to be thawing? For centuries after the last great ice age, temperatures climbed, glaciers retreated, and vast new landscapes opened for life to flourish. Then, with shocking speed, it all stopped. Around 12,800 years ago, the warming trend slammed into reverse. This sudden plunge back into icy conditions defines a geological chapter called the Younger Dryas, a 1,000-year winter that descended upon a planet expecting spring. To understand this mystery, scientists look not to the ice but to the dirt. Scattered across the globe, from North America to Europe and beyond, lies a specific razor-thin layer in the soil. It is known as the Younger Dryas Boundary. Think of it as a page in Earth's diary, a single line written in the language of chemistry and physics. This is not ordinary dirt. Within this dark stratum, researchers have found a bizarre collection of materials that simply do not belong. There are high concentrations of platinum, an element rare on Earth's surface but common in asteroids and comets. There are tiny diamonds formed only under immense pressure and heat. And there are microscopic beads of melted glass, called spherules, which look like cosmic raindrops frozen in time. This layer is a global crime scene, and the evidence points to a singular, violent event. Crucially, this boundary marks a line of profound loss. In the soil just below it, we find the fossils of magnificent creatures, the megafauna of the Ice Age. Mammoths, mastodons, giant ground sloths, and saber-toothed cats. Their remains vanish above that line. In North America, the sophisticated stone tools of the Clovis people, some of the continent's earliest known inhabitants, also disappear from the archaeological record at this exact moment. A way of life, honed over generations, seems to have been interrupted. The Younger Dryas Boundary acts as a timestamp, a moment frozen in sediment that separates two worlds. Below it, an Earth emerging from an ice age, teeming with giant creatures and early human cultures. Above it, a colder, emptier planet, where both the beasts and the people who hunted them are gone. This thin line of dirt is our first solid clue that something extraordinary happened, not in one valley or on one continent, but everywhere. It begs the question, what kind of event leaves a chemical fingerprint across the globe and resets the very climate of the planet? The hunt for an answer leads us from the ground beneath our feet to the sky above our heads. The evidence was not just chemical, it was physical. To find it, scientists had to look closer than ever before, sifting through ancient soil samples not for bones or tools, but for particles smaller than a grain of pollen. What they found was a microscopic treasure trove of catastrophe. Scattered within that dark Younger Dryas boundary layer were countless nanodiamonds. These are not the glittering gems in a jewelry store, but crystals formed only under the staggering pressures and searing temperatures of a cosmic collision. Their presence is a definitive signature, like finding tiny, hardened droplets of a star scattered across the Earth. Alongside them were other telltale fragments, magnetic and carbon spherules, all bearing the marks of a sudden, violent heating event. Think of it as forensic science on a planetary scale. If you were investigating an ancient, unexplained event and found spent bullet casings scattered uniformly across a continent, you would have compelling proof of a conflict. These microscopic materials are the cosmic equivalent, the spent casings from a celestial impact. Researchers like James and West led the charge, identifying these particles at multiple sites across North America, in Europe, and beyond. Their work transformed a theoretical idea into a tangible case. Finding such materials in one location could be a fluke, but finding the same unique fingerprint in the same thin layer of time, across oceans and continents, points to a single, global cause. This concrete evidence forces a dramatic shift in perspective. It moves the discussion from a slow climate change to a sudden, explosive intervention from space. The presence of nanodiamonds does not just suggest a comet might have been involved. It shouts that something with immense energy reshaped the atmosphere in an instant. This microscopic debris forms the bedrock of the theory, the undeniable clue that pushes us to ask the next, even more dramatic question. If the sky did fall, what exactly would that look like? And how could it plunge the world back into ice? But a chemical fingerprint needs a specific element to name the suspect. That crucial identification came from an element most of us associate with jewelry and catalytic converters: platinum. In the same thin, dark layer that held the microscopic diamonds, geologists made another startling discovery. They found concentrations of platinum and its cousin, iridium, that were hundreds of times higher than normal. This was the eureka moment. On Earth's surface, these elements are incredibly rare, buried deep within the planet's mantle. But in certain asteroids and comets, they are abundant. Finding a spike of them in a geological layer is like finding gunpowder residue at a crime scene. It points directly to an extraterrestrial source. We have seen this before. The most famous example is the iridium layer that marks the end of the age of dinosaurs, 66 million years ago, linked definitively to the massive impact in what is now Mexico. That layer became the golden standard, the proof that a cosmic event can leave a permanent, global signature in the rock record. The Platinum Anomaly at the Younger Dryas Boundary is a similar signal, a whisper from the past written in the language of the periodic table, and this whisper was heard around the world. Ice cores drilled from the remote glaciers of Greenland showed the spike. Sediment samples from lakes across Europe recorded it. The same unmistakable platinum signature appeared in North American sites, from California to the Carolinas. This was not a local event, like a forest fire or a volcanic eruption. This was a planetary signal, a dusting of cosmic material that settled uniformly across the globe. That global reach is what transforms a curious finding into a powerful hypothesis. It tells us that for a brief moment in time, 12,800 years ago, the atmosphere was seeded with dust from a disintegrating comet or asteroid. This geochemical evidence allows us to start modeling the scale of the event. We are not talking about a single, localized impact crater, though that may have been part of it. We are talking about an airburst or a series of airbursts, where a comet fragments in the atmosphere and explodes with the force of thousands of nuclear weapons, vaporizing itself and scattering its elemental essence across continents. The consequence of such an influx is almost beyond comprehension. It would have been a day of fire, followed by a long, cold night. The platinum dust settled, but the event had only just begun. With the evidence of a cosmic visitor now clear in the soil, we can reconstruct the terrifying sequence that likely followed. The leading hypothesis points not to a single, solid asteroid striking the ground, but to a fragmented comet. Imagine a mountain of ice and rock, perhaps originating from the meteor stream that still crosses our orbit today, hurtling toward Earth. As it entered the atmosphere, the immense pressure and heat would have caused it to shatter, like a pane of glass struck by a hammer. The result would not be one impact, but a cluster of them, a celestial shotgun blast across the sky. These fragments, some possibly miles across, would not have reached the ground intact. Instead, they would have detonated high in the atmosphere in cataclysmic explosions known as airbursts. An airburst releases all its devastating energy in the sky. The closest analog we have is a thermonuclear detonation, but on a scale far beyond any human weapon. A single fragment exploding could release energy equivalent to millions of tons of TNT, generating a blistering fireball that would instantly ignite forests and grasslands below. Followed by a supersonic shockwave that would flatten everything for hundreds of miles. The heat would be unimaginable, turning stone to glass and soil to ash in an instant. This scenario elegantly explains the global evidence, without requiring a single, obvious crater like the one that ended the dinosaurs. The destruction would have been widespread and horrifically uneven, a scattershot of devastation across continents. Researchers have proposed several candidate sites that could be scars from this event. The thousands of elliptical depressions known as the Carolina Bays, scattered across the southeastern United States, have long been debated as possible evidence of secondary impacts or the effects of the shockwave. More recently, the discovery of a large, buried crater under the Hiawatha Glacier in Greenland has offered another potential ground zero, suggesting a fragment may have indeed struck the ice sheet. Whether from direct hits or explosions, the effect would have been the same: a day of global fire that reset the course of life on Earth. The immediate aftermath of such an atmospheric bombardment would set in motion a chain of disasters, plunging the planet into a long, deep freeze. The sky itself became a furnace. Following the cataclysmic airbursts, the thermal radiation raining down would have instantly ignited anything flammable below. Vast stretches of North America, from the pine forests of the Pacific Northwest to the grasslands of the Great Plains, were likely transformed into a single, continent-spanning firestorm in a matter of hours. The ecological devastation is almost beyond words. Imagine a wall of flame so immense it creates its own weather, consuming the primary food source for the giant herbivores, and scorching the landscapes human cultures depended on for survival. The evidence for this is not just theoretical, it is written in the earth itself, in a distinct layer researchers call the black mat. This is a dark, organic-rich stratum found at numerous archaeological sites, and it consistently sits directly above the last traces of Clovis culture. Within this black mat, scientists find high concentrations of soot, charcoal, and fungal spores associated with widespread burning. It is a literal line of ash, a sedimentary tombstone for an era. For the Clovis people, this layer represents a stark and sudden cutoff. Their distinctive spear points, their campsites, their entire material culture disappears beneath this blanket of charcoal. It is as if a curtain fell at the climax of their story. The ecological holocaust was immediate, but the true planetary crisis was just beginning. All that burning created something far more dangerous than scorched earth. It filled the atmosphere with a shroud that would block the sun's warmth for generations. That shroud of soot and dust was the key to a deeper freeze. When the fires finally died, the atmosphere was choked with microscopic particles, a vast veil of debris lofted high into the stratosphere where winds could carry it around the globe. This is the mechanism of an impact winter. Sunlight that should have warmed the Earth was instead reflected back into space or absorbed by the floating haze. The planet's thermostat was effectively switched off. The result was not a gradual decline, but a climatic cliff. In some regions, like the North Atlantic, temperatures plummeted by as much as 10 degrees Celsius within just a few decades. For communities already reeling from the immediate destruction, This was a second, slower catastrophe. Spring simply did not return as expected, summer growing seasons shortened dramatically, and winter's grip tightened for 1,000 years. This abrupt plunge defines the Younger Dryas period, a geological anomaly that now had a terrifyingly clear potential trigger. The cooling was amplified by a critical disruption in the planet's circulatory system. The Atlantic Ocean operates a massive heat conveyor belt known as the Atlantic Meridional Overturning Circulation. Warm surface water travels north from the tropics, releasing its heat into the atmosphere over regions like Western Europe, before cooling, sinking, and flowing back south in the deep ocean. This system is a primary reason why places like Ireland have mild climates despite their northern latitude. The impact hypothesis suggests the sudden influx from the melting of the North American ice sheet, combined with the atmospheric chaos, could have stalled this vital current. If the conveyor belt slows or stops, the northward flow of tropical heat ceases, and northern latitudes plunge into deep cold independent of the global soot veil. It was a 1-2 punch, a rapid global cooling from atmospheric debris followed by a sustained regional freeze from a broken ocean pump. This prolonged environmental crisis created a world where survival became a daily struggle against the elements. For the great Ice Age mammals, the combination of lost habitat from the fires and a radically shifted climate proved insurmountable. Their populations, already stressed, likely collapsed under the pressure of a rapidly changing world they could not adapt to quickly enough. For human cultures like the Clovis, the challenge was existential. Their sophisticated toolkit was designed for hunting megafauna in a specific environment. When those animals vanished and the very landscape transformed, their entire economic and social foundation crumbled. Some groups may have migrated, fragmenting into smaller bands. Others may have faced hardships that left little trace in the archaeological record. The cosmic event did not necessarily vaporize every individual, but it shattered the ecological and climatic stability that their civilizations were built upon. This provides a powerful, unified explanation for two of prehistory's greatest mysteries: the simultaneous disappearance of the megafauna and the eclipse of early American cultures, not as separate events, but as intertwined consequences of a single bad day for planet Earth. Yet, could such a world-altering catastrophe have left an echo in human memory itself? The story of the Clovis people ends abruptly in a layer of black earth. At places like Draw in New Mexico, one of the most significant Clovis sites ever found, the stratigraphy tells a silent, stark tale. In the lower levels, archaeologists uncover a wealth of beautifully crafted fluted spear points, tools for processing game, and the remains of mammoths and other large animals. Then, there is a distinct line. Above it lies a thick, dark stratum of organic material, the black mat. In that layer, the Clovis artifacts vanish. No more spear points, no more evidence of their distinctive campsites. It is as if a cultural signal, once strong and clear, was suddenly switched off. This presents one of North America's greatest archaeological puzzles. What happened to these sophisticated people who had mastered their environment for centuries? The traditional debate offers several possibilities. Perhaps they did not vanish at all, but simply adapted their technology to a changing world, their later tools becoming unrecognizable to us. Maybe they migrated, fragmenting into smaller groups and moving to new territories. Or, the most difficult possibility to consider, did they face challenges that led to their decline? The comet impact theory enters this debate as a powerful, yet controversial, explanation. For some researchers, the global evidence provides a compelling reason for that sudden break in the archaeological record. The proposed sequence of firestorms, climate collapse, and the loss of their primary food sources could have shattered their way of life in a generation. It reframes their disappearance not as a failure to adapt, but as a response to an unimaginable external catastrophe. Other archaeologists urge caution. They point out that cultural change is complex, and pinning the entire transformation of a continent's human history to a single event can oversimplify the story. They argue that the Clovis technology itself was already evolving before the Younger Dryas, and that the black mat represents an environmental change that people weathered by innovating, not disappearing. This scholarly discussion is vital because the fate of the Clovis is a microcosm of the larger, haunting question. If a well-established, geographically widespread culture could be so profoundly disrupted, what about other societies existing at the same precarious moment in history? This curiosity pushes our search beyond North America to see if threads of a similar story are woven into the ruins of other ancient worlds. Far to the east, on a windswept hill in southeastern Turkey, a different kind of evidence stands in silent testimony. This is a complex of massive stone circles erected around 11,500 years ago, a mere few centuries after the proposed cosmic event. Its discovery shattered long-held assumptions about human development. Here, before the invention of pottery or metal, before the establishment of permanent agriculture or cities, people came together to quarry, carve, and erect pillars weighing up to 20 tons. The sophistication is staggering, a monument that seems to belong to a later age, yet it was built by those who lived in the direct shadow of the Younger Dryas. The timing is provocative. Does not date to a period of settled farming prosperity, but to a time of profound climatic stress and ecological recovery. This has led some researchers and authors to propose a radical idea that is not merely a temple, but a memorial. They suggest its construction was a communal response to a shared trauma, a gathering of survivors to make sense of a world that had nearly ended. The iconography carved into the limestone pillars fuels this interpretation. The central T-shaped monolith, some argue, could represent stylized human forms, perhaps ancestors or guardians. More strikingly, the reliefs covering the pillars are dominated not by scenes of abundance, but by a menagerie of dangerous and powerful animals, scorpions, snakes, lions, and vultures. These creatures are often depicted in dynamic, aggressive poses. Some researchers see in these carvings a record of a time of chaos, a world out of balance where the natural order turned hostile. A few have even proposed that certain symbols, like the crescent and circle motifs, could represent celestial phenomena, a preserved memory of a comet in the sky. While mainstream archaeology cautions against literal interpretations of prehistoric art, the emotional tone of the site is hard to ignore. The effort required to build speaks of a powerful, unifying purpose. In the wake of a global catastrophe, what would bring scattered bands of hunter-gatherers together to undertake such a backbreaking, generational project? Perhaps it was the need to re-establish order, to create a fixed point in a changed world, to honor what was lost and plead for stability from the forces that governed their universe. The site challenges the old narrative of a slow, linear progression from simple to complex societies. Instead, it hints at a flash of cultural brilliance, a rapid reorganization of human labor and belief, possibly driven by the need to cope with a shared existential shock. This raises a profound question about human resilience. If a cataclysm did occur, could detailed knowledge of it have been preserved not in writing, but in story, passed down through hundreds of generations until it was etched into stone as myth and warning? The stones stand as a silent question mark at the dawn of our remembered history. Silent stones pose a question that echoes through time. If a civilization-altering event truly occurred, could its memory have survived not in sediment, but in story? When we step back and survey the world's oldest recorded narratives, a startling pattern emerges. From the banks of the Tigris and Euphrates to the highlands of the Andes, cultures separated by vast oceans share a common thread: tales of a great deluge. The Mesopotamian epic of Gilgamesh, one of humanity's oldest written stories, describes a world-engulfing flood sent by angry gods, with a chosen survivor building a boat to preserve life. Similar stories resonate in the Hebrew Bible, in Hindu scriptures, and in the oral traditions of indigenous peoples across the Americas. Often intertwined with these flood narratives are other cataclysmic motifs: fire raining from the sky, a long darkness, and a bitter cold that gripped the world. The Greek philosopher Plato, writing much later, recounted the legend of Atlantis, a sophisticated civilization that sank beneath the waves in a single day and night of misfortune. Scholars have long debated the origins of these ubiquitous myths. Some see them as allegories for moral or spiritual renewal, or as distant memories of localized river floods. Yet their sheer global prevalence and their consistent pairing with celestial fire and climatic collapse invite a different interpretation. Could they be the fragmented, poetic echoes of a real, global catastrophe, passed down from those who witnessed it? The psychological impact of such an event would be immeasurable. For generations who understood the world through the lens of divine agency, a sky that turned to fire and a climate that inexplicably reversed would seem like the ultimate punishment or a cosmic reset. The trauma would embed itself deep in the collective consciousness, becoming a foundational story about the fragility of human endeavor and the power of nature. This is where the comet impact theory makes a profound bridge between hard science and human experience. The geological evidence, the platinum layer, the nanodiamonds, and the black mat provide a potential physical anchor for these ancient stories. They offer a scenario where the myths could be rooted in a real historical event, distorted by time and retelling, but preserving a core truth: the sky fell, the waters rose, and the world was remade. This connection does not prove the myths are literal accounts, but it suggests they are not mere fiction either. They may be humanity's first attempt at historiography, a way of encoding a generation-defining trauma into a cultural memory that could warn and guide their descendants. It transforms these stories from curious folklore into potential testimonies, urging us to listen more closely to the old tales, not just for their moral lessons, but for the whispers of ancient weather reports written in the language of gods and monsters. This thematic link enriches the scientific theory with a deeply human dimension, proposing that our oldest stories might be a key to unlocking one of our planet's oldest cold cases. The whispers of myth and stone find a chilling echo in the coldest places on Earth. Far from the ruins of the Black Mat sites, a pristine record of our planet's past is locked in mile-thick ice. In the remote, frozen heart of Greenland, scientists drill deep into the glaciers, extracting cylinders of ancient ice like pages from a climate diary. Each annual layer compressed over holds tiny bubbles of the atmosphere as it was, along with dust, volcanic ash, and chemical signatures of long-vanished events. These ice cores provide an independent timeline, a year-by-year account of Earth's environmental health, and at the depth corresponding to 12,800 years ago, the record shows a violent spike. Researchers analyzing these cores found an enormous increase in ammonium, alongside elevated levels of nitrate. In the chemistry of ice, These compounds are the telltale signs of fire on a continental scale. Ammonium is released in vast quantities from the burning of biomass, like forests and grasslands. This spike is not a small fluctuation. It is a dramatic anomaly that stands out starkly against the backdrop of natural variation. It paints a picture of a world suddenly and catastrophically on fire. The ice does not tell us why the fires started, but it corroborates the story written in the terrestrial black mat. It suggests the burning was not local, but widespread enough to pump its chemical signature high into the global atmosphere, where winds carried it all the way to the polar ice caps and sealed it in time. This independent line of evidence is crucial. It bridges the gap between the geological finds on the ground and the broader climate story. The Greenland ice cores offer a snapshot of the global atmosphere in the immediate aftermath of the proposed event, and that snapshot shows a planet shrouded in the smoke of its own burning. It transforms the theory from a collection of regional clues into a coherent global narrative, where evidence from the soil, the stones, and now the very air itself begins to converge on a single catastrophic moment. Yet for every compelling theory, science demands a rigorous debate. Not all researchers are convinced the evidence points solely to the stars. A powerful alternative explanation lies closer to home, deep within the Earth itself. Could the dramatic cooling of the Younger Dryas, and even some of the strange geochemical signals, be the work of massive volcanic eruptions rather than a cosmic impact? This skeptical viewpoint is crucial because it forces the impact hypothesis to defend its evidence against other plausible causes. The most prominent candidate in this volcanic alternative is an event that occurred in what is now Germany, around the same pivotal moment. The sea volcano erupted with colossal force, an explosion estimated to be many times more powerful than the 1980 eruption of Mount St. Helens. It would have devastated Central Europe, blanketing the region in ash and pumping vast quantities of sulfur dioxide and other aerosols high into the stratosphere. These aerosols are known to reflect sunlight, and a sufficiently large eruption could potentially trigger a period of global cooling, offering a purely terrestrial explanation for the sudden cold snap. Furthermore, volcanic activity can produce some of the materials found in the Younger Dryas Boundary layer. Certain types of, for instance, can form in the intense heat of a volcanic plume. So on the surface, the volcanic hypothesis presents a clean, earthbound answer. But when we scrutinize the details, the comparison becomes more complex. The unique fingerprints at the heart of the impact theory start to diverge from a purely volcanic story. Take nanodiamonds, for example. While extreme geological processes can create diamonds, the specific types and abundances of nanodiamonds found globally in the Younger Dryas layer are far more consistent with the shock pressures of an extraterrestrial impact. Similarly, the global distribution of the evidence is a significant hurdle for the volcanic explanation. The platinum and iridium spikes, the nanodiamonds, and the unique spherules are found across multiple continents, from North America to Europe and the Middle East. A single volcanic eruption, even one as massive as C, would struggle to distribute its ejecta so uniformly around the entire planet. Its fingerprint would be strongest near the source and fade with distance, not appear with striking consistency in sites thousands of miles apart. This critical examination does not dismiss the volcanic alternative, but it carefully weighs its explanatory power. It acknowledges that the Earth is a dynamic, violent place capable of its own catastrophes. The sea eruption undoubtedly happened and affected the climate of its time. Yet, the global scale and the specific cocktail of extraterrestrial materials point toward an event with a different origin. This ongoing debate is not a weakness of the science, but its greatest strength. It ensures that the comet impact theory is continually tested and refined, forced to account for every detail and answer every challenge. The conversation between these competing ideas is what sharpens our understanding of humanity's deep past, reminding us that the most profound mysteries are rarely solved by a single, simple answer. The loss was staggering in both scale and speed. Across North America alone, more than 35 entire genera of large animals vanished from the fossil record. This was not just the end of the woolly mammoth and the mastodon. It was the disappearance of an entire world, a lost menagerie that included the saber-toothed cat, the giant short-faced bear, the massive dire wolf, the American lion, and ponderous creatures like the giant ground sloth. For over a century, scientists have fiercely debated what caused this extinction event, a puzzle with two primary suspects. The first is the overkill hypothesis, which suggests that as highly skilled human hunters like the Clovis people spread across the continent, they hunted these naive animals to extinction. The second is climate change, arguing that the warming world at the end of the Ice Age simply altered habitats too quickly for these specialized giants to adapt. Both theories have compelling points, but also significant holes. Human hunters were certainly present, but the archaeological evidence of mass killings is sparse. The climate was indeed changing, but these animals had survived multiple glacial cycles before. This is where the comet impact theory enters the debate, not necessarily to replace these ideas, but to combine them into a perfect storm. It proposes a sudden, catastrophic trigger that amplified both hunting pressure and environmental stress to a breaking point. Imagine a population of mammoths already facing a shifting climate. Then, in a matter of days, continent-spanning firestorms incinerate their grazing lands. A pall of dust and soot plunges temperatures, stunting the regrowth of plants. The surviving herds, now concentrated around the few remaining water sources and patches of greenery, would have become tragically easy targets for human hunters who were themselves desperate for food. The impact does not argue that humans or climate alone killed the megafauna, but that the comet created conditions where both became exponentially more lethal. This synergy helps explain the rapid, synchronous nature of the extinctions across continents, a global event that pure climate or human models struggle to fully account for. The evidence for this sudden disturbance is sometimes written in the animals themselves. In places like Alaska, there are deposits known as the muck pits, where the frozen remains of mammoths, bison, and other creatures are found jumbled together in a chaotic mass, often alongside uprooted trees and layers of silt. Some interpretations suggest these were animals caught in catastrophic mudflows or flash floods, potentially triggered by the sudden melting of permafrost or ice in the violent aftermath of an impact event. These frozen graveyards paint a picture not of a slow decline, but of a violent, abrupt end. The iconic image of the woolly mammoth, therefore, becomes more than a symbol of the Ice Age. It becomes a potential witness. Its widespread and relatively sudden disappearance serves as a powerful marker in time, a biological confirmation that something extraordinary happened. The comet impact theory provides a unified mechanism that connects the geological clues, the archaeological disappearance, and the biological catastrophe into a single, coherent narrative. It suggests that the great beasts of the ancient world did not fade away gently, but were likely brought down by a 1-2 punch from earth and sky. A reminder of how fragile even the most dominant life can be when the rules of the world are rewritten overnight. We stand at the edge of a profound question about our own story. For generations, the timeline of human progress seemed elegantly simple. First, we were nomadic hunter-gatherers for tens of thousands of years. Then, around 10,000 years ago, we invented agriculture in the Fertile Crescent, which allowed us to build permanent settlements, which led to cities, writing, and civilization as we know it. It is a clean, upward march from simplicity to complexity. But what if that timeline is wrong, or at least incomplete? The evidence of a global catastrophe 12,800 years ago forces us to reconsider a radical possibility. Could there have been advanced Ice Age civilizations, societies of significant cultural and intellectual achievement that were simply erased from the record by the comet's aftermath? This is not about finding Atlantis on a map, but about re-examining the very definition of advanced. We tend to measure advancement by technology, by metallurgy and written records. Yet, a society could be advanced in other ways, possessing deep astronomical knowledge encoded in myth, sophisticated understanding of monumental architecture using only stone, or intricate navigational skills to traverse oceans. Such knowledge, passed down orally or through ephemeral materials, would leave little trace for archaeologists, especially if the people who held it were scattered or their world was submerged. Consider the enigmatic site of Padang in Indonesia. What appears as a hill is believed by some researchers to be a massive, multi-layered pyramid, with the deepest structures potentially dating back more than 20,000 years. The official narrative places its construction much later, but the controversy itself highlights our struggle to date megalithic sites accurately. If even a fraction of the older dates are correct, it suggests people were organizing labor and shaping landscapes on a grand scale long before we thought possible. Then there is in Turkey, a vast Neolithic city dating to around 9,000 years ago. Its discovery revealed a society without streets, where people moved across rooftops and buried their ancestors beneath the floors of their homes. Displaying a complex symbolic and social structure that seems to emerge fully formed, without clear precedent, where did this cultural complexity come from? Could it be the flowering of surviving knowledge from an earlier, traumatized world? The comet impact theory provides a compelling context for this idea. It proposes a reset event, a bottleneck not just for species, but for human cultural development. A cataclysm of that scale would not only destroy settlements and reduce populations, it would sever the continuity of knowledge. Survivors would be thrust into a centuries-long struggle for mere survival in a darkened, colder world. The meticulous understanding of star cycles used for navigation or calendar keeping, the architectural techniques for building with massive stones, the social structures for governing large groups. All of this hard-won knowledge could become a luxury, then a memory, then a forgotten dream within a few generations. The priority shifts from building monuments to finding the next meal. This resets the cultural clock, forcing humanity to slowly rebuild not just its numbers, but its collective intelligence from a much lower baseline. What we call the dawn of civilization, then, may not be a beginning but a rebirth. It challenges us to look at the scattered, anomalous ruins and ancient myths not as isolated curiosities, but as possible fragments of a much older story, a story that ended when the sky fell. This line of thinking naturally draws our gaze to the most likely repository for such lost chapters, not on the hills, but beneath the waves, where rising seas at the end of the ice age may have swallowed entire coastal worlds. The coastline of our world was once a very different place. During the last ice age, so much water was locked up in continental ice sheets that global sea levels were over 100 meters lower than they are today. This exposed vast plains that are now submerged, creating land bridges and habitable territories that have since vanished beneath the waves. Two of the most significant are known to researchers as and their stories add a profound geographical dimension to the mystery of lost Ice Age societies. Was a massive subcontinent, connecting the islands of Indonesia, Malaysia, and Borneo to mainland Southeast Asia. It was an area larger than India, a tropical expanse of rainforests, rivers, and rolling hills that could have supported a large human population. To the northwest, in what is now the North Sea between Great Britain and Denmark, stretched a fertile, low-lying plain of marshes, lagoons, and rolling hills, teeming with game and rich in resources. These were not barren wastelands, but vibrant, populated landscapes. We know this from the trawlers that occasionally dredge up startling reminders from the. In the North Sea, fishermen have for decades pulled up ancient bones of mammoths, reindeer, and lions, alongside human artifacts, finely crafted bone tools, and antler harpoons left by Mesolithic hunters. These finds confirm that was a heartland, not a periphery, for thousands of years. Then, the waters returned. As the Ice Age ended, the glaciers melted and the oceans rose. This process, called glacial meltwater pulse, was generally steady, but is believed to have included periods of extremely rapid sea level rise. Here is where the comet impact theory introduces a provocative possibility. The proposed climate chaos of the Younger Dryas, with its sudden warming and cooling cycles, could have triggered catastrophic glacial melt and destabilized ice dams, causing massive, sudden pulses of to pour into the oceans. Such an event would not have been a gentle, inch-by-inch creep, but a rapid, relentless invasion. For the communities living on these coastal plains, the change would have been terrifyingly visible. Generations might have watched their familiar hunting grounds slowly shrink, then seen the waters advance accelerate into a rout, swallowing forests, hills, and sacred sites within a human lifetime. The slow drowning of a continent became, potentially, a rapid inundation. Modern technology allows us to map these lost worlds. Sonar surveys of the have revealed the ghostly topography of in stunning detail, showing the winding courses of ancient rivers like the river and the outlines of vast lagoons and coastlines. These are the drowned landscapes of a once thriving ecosystem. The implication is haunting. If we accept that these now submerged plains were prime territories for human settlement, then the most archaeologically rich areas of that ancient world, the places where people would have congregated along rivers and coastlines, are precisely the areas now deepest underwater. Our entire understanding of prehistory is biased toward what survived on higher ground, in caves and inland sites. The cradles of early society may not be in the hills we can dig, but on the continental shelves we have only begun to scan. This transforms the mystery from one of mere disappearance to one of displacement and profound loss. A coastal culture with sophisticated knowledge of tides, stars, and maritime resources would have had its entire identity and history erased as its homeland sank. Their stories, their innovations, and their very presence could have been swallowed by the sea, leaving only the faintest traces in the myths of later peoples who remembered a great flood. The search for our past, therefore, may be looking in the wrong place, focusing on the lands that remained while the true centers of ancient life lie silent and submerged. Holding their secrets under tons of water and sediment, stretching from New Jersey down to Florida, the landscape holds a secret written in its very shape. Scattered across the Atlantic coastal plain are hundreds of thousands of shallow, elliptical depressions known as the Carolina Bays. Seen from above, they form a stunning pattern, like a vast field of overlapping footprints pressed into the earth, all uniformly aligned in a northwest to southeast direction. Their sheer number is staggering, with estimates ranging from 500,000 to over 2 million. For decades, their origin has been a subject of intense debate, and they have become a focal point in the comet impact mystery. The most controversial hypothesis suggests these bays are not the work of slow geological processes, but the scars of a sudden, violent event. Proponents of the impact theory point to their peculiar alignment and shape. If a fragmented comet approached from the northeast and exploded in a series of airbursts, or if smaller fragments struck the ground at a shallow angle, they could have gouged out these elliptical basins and splashed material into the raised rims that still surround them. The consistent orientation would then act like a compass, pointing back to the source of the catastrophe in the sky. It is a compelling visual argument, a landscape seemingly frozen in the moment of a cosmic shotgun blast. Mainstream geologists, however, offer a more terrestrial, gradual explanation. The prevailing theory is that these bays are thermokarst features, formed over during the last ice age. In this model, patches of permafrost created impermeable lenses in the sandy soil. During warmer periods, these icy lenses would melt, causing the ground above to collapse and form a pond. Prevailing winds from the northwest would then shape these ponds into their current elliptical forms, elongating them and building up sand on the southeastern rims, much like a desert oasis shaped by persistent wind. This process is slow, requiring no catastrophic intervention from space. The scientific disagreement is a perfect example of how the same evidence can be interpreted in radically different ways. One side sees a landscape sculpted in an instant by fire from the heavens. The other sees a patient artwork created by the slow forces of ice, water, and wind over thousands of years. Whether they are impact scars or wind-blown ponds, the Carolina Bays contribute something vital to the larger story. They are a geological oddity that exists in the right place at the right time, their formation broadly coinciding with the Younger Dryas Boundary. Their presence encourages a broader perspective, urging us to look for similar enigmatic features elsewhere on the globe. And when we do, we find them, from the oriented lakes of Alaska to the paternoster lakes of the Andes. This global pattern of aligned depressions suggests that whether the cause was cosmic or climatic, something profound affected the shape of our planet's surface in that era. The bays stand as a permanent question mark on the landscape, a reminder that some of Earth's most common features might hold the key to its most uncommon days. Beneath the relentless ice of northwest Greenland, a hidden shape waits. In 2018, scientists analyzing radar data from NASA's Operation Icebridge made a staggering discovery. Under the massive Hiawatha Glacier, more than 2 kilometers of solid ice concealed what appeared to be a perfectly circular depression over 30 kilometers wide. The radar images revealed a classic bowl-shaped structure with a raised rim and a central peak, a textbook signature of a colossal impact crater. This was not an ancient, weathered scar, but a remarkably pristine formation, suggesting it could be geologically young. The immediate, electrifying question was, how young? If this crater could be dated to around 12,800 years ago, it would provide the missing physical evidence, a ground zero for the comet impact hypothesis. Here was a potential smoking gun, buried under the world's second-largest ice sheet. The discovery sent a shockwave through the scientific community, transforming a theory built on microscopic clues into a search for a single, monumental wound on the planet's surface. Investigating a crater under 2 kilometers of ice is a feat of modern polar exploration. Researchers cannot simply dig down to the bedrock. Instead, they must use indirect methods, like analyzing sediments washed out from under the glacier by meltwater. Early studies of these sands and gravels showed shocked quartz and other minerals deformed by immense pressure, further evidence of an impact. But the crucial task of precise dating remains an immense challenge. The ice itself offers clues, as the layers above the crater were disturbed, but the definitive answer lies in testing the rocks of the crater floor directly, a task that may require drilling through the entire ice cap. The Hiawatha crater represents the tantalizing frontier of this mystery. It embodies the human drive to find a definitive answer, to replace a compelling "what if" with a concrete "where." A confirmed impact of that size at that precise time would elegantly explain the global fallout, the fires, and the climate shock. It would connect the microscopic diamonds scattered across continents to a single, catastrophic point of origin. Until the dating is conclusive, the crater remains a powerful symbol of possibility, a ghostly outline on a radar screen that holds the potential to rewrite our deepest past. It reminds us that some of Earth's greatest secrets are not lost to time, but simply waiting, preserved in the planet's most frozen and inaccessible vaults. The search for a definitive date is a race against time itself. In both archaeology and geology, the timeline is everything, the framework upon which all explanations must hang. For a theory proposing a single, world-altering event, the need for a precise chronological anchor is absolute. Yet this is where the investigation confronts one of its most persistent challenges, the inherent limitations of our historical clocks. The primary tool for dating organic remains from this period is radiocarbon dating, a method that measures the decay of a radioactive isotope in once living material. It is remarkably reliable, but around the time of the Younger Dryas onset, the calibration curve hits what scientists call a plateau. This means that for several centuries, the amount of radioactive carbon in the atmosphere was relatively stable, causing radiocarbon dates from that entire span to cluster together. It is like trying to read a clock with a minute hand that barely moves. You know you are within a certain window of time, but pinpointing the exact year, or even decade, becomes incredibly difficult. This plateau creates a chronological fog, a several hundred-year period where events can be hard to sequence with the fine resolution we desperately need. Did the fires start before the cooling, or was it the other way around? The radiocarbon clock struggles to tell us. To cut through this fog, researchers turn to other, more globally synchronous markers. This is where the platinum spike itself becomes a potential dating tool. Because the layer containing the extraterrestrial dust appears to have been deposited rapidly and simultaneously across the globe, finding it at an archaeological site can act as a precise timestamp. A moment frozen in chemistry. Similarly, layers of volcanic ash from a known, well-dated eruption can serve as another kind of clock. If that same ash layer is found above the platinum layer at one site and below it at another, it helps bracket the event in time. These methods allow scientists to weave a more precise tapestry of cause and effect. The debate often hinges on these technical details. A discrepancy of even a century in the dating of a key site can allow skeptics to argue that the proposed impact did not align with the cultural changes or extinctions, that it was merely background noise rather than a decisive blow. Proponents, in turn, work to refine the dates, to demonstrate that the platinum layer, the charcoal from the fires, and the last artifacts of the Clovis culture all converge on the same narrow band of time. This meticulous, often contentious work is the unglamorous backbone of historical science. It reminds us that reconstructing deep history is an exercise in patience and precision, a form of detective work where the evidence is fragmented and the witnesses are silent. Each new dating technique, each refined analysis of an ice core or sediment layer, is another attempt to sharpen our blurred picture of the past. We are walking a chronological tightrope, balancing what we know with what we can prove, inching closer to the moment when the world may have changed forever. This grand puzzle cannot be solved by a single key. The true power of the comet impact theory lies not in one field of study, but in the convergence of many. It is a story that demands astronomers to model the chaotic orbits of ancient comets, geologists to sift through microscopic grains of soil, and archaeologists to interpret the silent stories told by stone tools and ancient hearths. Each discipline brings a different piece of the picture, and only when they are laid side by side does a coherent image begin to form. This is the essence of interdisciplinary science, a collaborative detective story on a planetary scale. A landmark moment in this collaboration came in 2018, with a major paper published in the journal Scientific Reports. This study did not present a single new discovery, but instead wove together threads of evidence from across the globe. It synthesized the data on platinum spikes from ice cores, the distribution of nanodiamonds from multiple continents, and the chronological placement of the black mat at archaeological sites. By compiling these disparate lines of evidence, the paper constructed a far more robust argument than any single finding could achieve alone. It demonstrated that the signal was not a local anomaly, but a global pattern, a chorus of data points all singing the same song. This synthesis creates a narrative that is greater than the sum of its parts. An astronomer can tell us a comet could have come from the stream, but cannot prove it touched the Earth. A geologist can show us the platinum in the soil, but cannot tell us what it meant for the people who lived there. An archaeologist can document the disappearance of a culture, but cannot alone identify the force that caused it. When their work is integrated, however, a powerful and complex story emerges, one that acknowledges both the physical catastrophe and the human experience of it. This holistic approach is the future of investigating humanity's deepest mysteries. It moves us beyond isolated specialties and toward a unified understanding of our past. It demonstrates a fundamental truth that no single science holds all the answers, especially for an event that reshaped the world from the atmosphere down to the archaeological record. As we now turn to examine the profound cultural impacts of such an event, this principle of interconnected understanding will be our most essential guide. The potential erasure of entire Ice Age societies forces a humbling reflection on the nature of civilization itself. It suggests that complexity and achievement are not guarantees of permanence, that even thriving cultures exist in a delicate balance with their environment. This ancient story transforms the comet impact theory from a fascinating historical puzzle into a profound lesson in vulnerability. It reveals that our ancestors, for all their ingenuity, were profoundly susceptible to shocks from a global system they could neither predict nor control. Their experience underscores a fundamental truth that sudden environmental change can act as a great leveler, reshaping human destiny in a geological instant. Yet within that vulnerability lies an equally powerful testament to resilience. While some communities may have faced overwhelming hardship, others clearly found a way forward. The monumental effort of rising from the ashes of that chaotic period is not a monument to despair, but to determination. It represents a conscious choice to rebuild meaning, to gather scattered survivors, and to create something enduring in a world that had proven terrifyingly fragile. This duality, the capacity for both collapse and recovery, is the deepest human lesson etched into this 12,000-year-old event. It shows us that catastrophe can be a catalyst for cultural reinvention, as much as for dissolution. The survivors did not merely persist, they synthesized their trauma into new forms of social organization, spiritual expression, and technological adaptation. They carried forward the essential spark of knowledge, community, and hope, proving that while a civilization can be interrupted, the human capacity to rebuild is remarkably tenacious. This ancient precedent carries urgent relevance for our own era. Today, we face our own set of global-scale vulnerabilities, from the gradual pressures of climate change to the sudden, existential threat of a future asteroid impact. The difference, of course, is awareness. We are not passive inhabitants of our planet. We are its conscious stewards with the tools to see these threats coming. The story of the Younger Dryas impact is a stark reminder of why programs like NASA's Planetary Defense Coordination Office are not science fiction, but critical exercises in planetary stewardship. It validates the very real need to track near-Earth objects and develop technologies to deflect them, transforming a prehistoric tragedy into a modern imperative for survival. Similarly, the climatic aftermath of the ancient event mirrors, in a compressed and violent form, the disruptive power of rapid environmental shift. It demonstrates how interconnected Earth systems are, how an event on one continent can trigger cascading failures across the globe, affecting weather patterns, ocean currents, and food security. Understanding this deep-time example of climate shock gives historical depth to our current crisis, emphasizing that the stability we depend upon is not a default state, but a precious and potentially fragile equilibrium. Ultimately, this journey into a possible lost chapter of human history is not about proving a single catastrophic day, but about broadening our understanding of human endurance. It challenges the linear narrative of inevitable progress and replaces it with a more cyclical story of challenge, adaptation, and renewal. The stones of the silent strata of the black mat and the global whisper of platinum dust together ask us a pressing question, not about the past, but about the future. If our ancestors could rally and rebuild after a sky of fire and a 1,000-year winter, what does that say about our own responsibility and our own potential to safeguard and renew our world today? The lesson is clear. Resilience is not just about surviving the blow, but about remembering how to stand together and build anew when the dust finally settles. Our planet's journey through space is far from a solitary voyage. Earth orbits the Sun within a dynamic and often crowded neighborhood, a celestial shooting gallery filled with asteroids and the icy debris of ancient comets. This cosmic context transforms the Younger Dryas event from a possible freak accident into a potential chapter in a much longer cyclical story. The evidence points us toward a specific suspect, the meteor stream. This vast river of cosmic debris, which our planet passes through twice each year, is believed by some astronomers to be the scattered remains of a giant comet that broke apart tens of thousands of years ago. Within this stream, researchers hypothesize the existence of a dense cluster of larger fragments, a swarm of potential city killers or continent shakers that Earth might encounter only every few thousand years. If the comet that potentially struck 12,800 years ago was a fragment from this stream, then the event was not a singular anomaly, but part of a recurring pattern. A periodic reminder of our vulnerability to the cosmos. This realization shifts the entire investigation from a historical curiosity into a matter of urgent, practical foresight. It frames the study of the Younger Dryas impact as a crucial case study, a drill from the past that prepares us for threats in the future. We are no longer passive passengers on a safe planet, but active crew members on a vessel sailing through a field of icebergs, some of which we are only beginning to map. This is precisely why modern astronomy has moved beyond mere observation to active planetary defense. Initiatives like NASA's Planetary Defense Coordination Office exist not as science fiction, but as a direct response to this understood cyclical threat. Their mission is to find, track, and characterize near-Earth objects, calculating their orbits centuries into the future to identify any potential dangers. They are, in essence, building an early warning system for our entire civilization, turning the lessons of deep time into actionable protocols for survival. The work involves incredible precision, using ground-based telescopes and space observatories to catalog hundreds of thousands of asteroids, watching for the one whose path might intersect our own. Beyond detection, scientists are seriously researching deflection technologies, methods to nudge a threatening object off course years or decades before a potential impact. These include concepts like kinetic impactors, which would slam a spacecraft into an asteroid to alter its speed, or gravity tractors, which would use a spacecraft's own minute gravitational pull to slowly tow an object onto a safer path. Each of these projects is a direct legacy of understanding that what happened once can, and statistically will, happen again. The ancient impact theory provides the historical justification for these monumental efforts, answering the critical question of why we should invest so much in guarding against such a seemingly remote possibility. It shows us that remote possibilities have shaped our world before. Therefore, peering into the murky past of the Younger Dryas is not an escape from modern concerns, but a profound engagement with them. It teaches us about the interconnectedness of cosmic events and earthly survival, about the fragility of complex systems, and about the long arc of human resilience. By deciphering the clues left in the dirt, the ice, and the stones, we are not just solving an ancient mystery, we are reading a survival manual written in the geological record. The platinum layer and the nanodiamonds are more than scientific curiosities. They are pages from that manual, urging us to look up, to prepare, and to remember that our future security depends on understanding the full story of our past, a story that is written not only on Earth, but in the stars themselves. Every revolutionary idea must face the courtroom of its peers, and the comet impact theory is no exception. To understand its true weight, we must listen carefully to its most thoughtful critics, for their skepticism is not an obstacle to truth, but the very process by which truth is refined. Prominent archaeologists and geologists have raised substantial challenges, arguing that the leap from physical evidence to a lost Ice Age civilization is a bridge too far, built on speculative interpretation. They point out, quite rightly, that evidence like the oriented lakes known as the Carolina Bays have compelling terrestrial explanations involving wind, water, and ancient permafrost. With no need for a celestial trigger, even some of the key impact markers are contested. Critics note that the tiny nanodiamonds, while compelling, can also form in the extreme pressures of lightning strikes or accumulate slowly from the steady rain of cosmic dust onto the planet's surface. Their presence alone does not automatically prove a single, cataclysmic airburst. On the cultural side, many archaeologists see the story of the Clovis people not as a sudden disappearance, but as a gradual transition. They argue that the Clovis point technology evolved into other, later styles, and that the population may have shifted its strategies and territories in response to slower environmental changes. Leaving a fragmented but not terminated archaeological record, this perspective urges caution against compressing complex, centuries-long human adaptations into the timeline of a single disastrous day. These critiques are not dismissals, they are essential counterweights. They force proponents to dig deeper, to date their samples with even more precision, and to rule out every other possible explanation. This back and forth is the scientific method in its form, a collaborative and often contentious effort to separate a dazzling story from demonstrable fact. The debate itself becomes a fascinating case study in how knowledge advances. A bold new hypothesis emerges, makes predictions, and gathers evidence. The wider community then subjects every piece of that evidence to intense scrutiny, searching for flaws in the logic or gaps in the data. For the theory to survive, it must answer these challenges convincingly. This process ensures that only the most robust ideas earn a place in our understanding of history, having been tempered in the fires of rigorous debate. So, while the image of a sky filled with fire and a world remade is powerfully compelling, the healthy skepticism of the scientific community acts as a necessary anchor, keeping the search for answers grounded in meticulous evidence rather than unchecked speculation. This dynamic tension between discovery and doubt is what ultimately leads us closer to the truth of our deep past, reminding us that the most enduring stories are those that can withstand the hardest questions. The debate thrives on a foundation of hard evidence, and today that evidence is being gathered with tools our scientific forebears could scarcely dream of. This is not a story of dusty libraries alone, but of laser pulses from aircraft and sensors that can read the chemical whispers of a single grain of soil. Modern technology is revolutionizing the search, transforming a theoretical puzzle into a quantifiable detective story. One of the most powerful new eyes in the sky is LiDAR, or light detection and ranging. Mounted on planes or drones, LiDAR scanners fire millions of laser pulses at the ground, penetrating dense forest canopies to map the bare earth beneath. It is like peeling back a green blanket to reveal the hidden furniture of an ancient landscape. Across Central America, LiDAR has unveiled vast, interconnected Maya cities hidden for centuries in the jungle. In the search for lost Ice Age worlds, this technology promises to map those submerged continental shelves and with stunning clarity, potentially revealing the ghostly outlines of river channels, campsites, or even monumental structures now resting on the. It allows us to survey in hours what would take ground teams lifetimes, guiding excavations to the most promising targets. On the ground, the toolkit has become equally sophisticated. Portable XRF analyzers, handheld devices that look like scanners, allow researchers to perform instant, destructive chemical analysis on site. A scientist can now point such a device at a layer of soil, and within seconds detect elevated levels of platinum or iridium, the very fingerprints of a cosmic event. This turns what was once a slow process of sample collection and lab analysis into an immediate field test, enabling teams to follow geochemical trails in real time. In the laboratory, advanced mass spectrometry has reached incredible sensitivity. These instruments can detect and measure trace elements and isotopes at concentrations as low as a few parts per trillion. They are the ultimate forensic tools, capable of distinguishing between terrestrial and extraterrestrial sources of materials, or dating minute samples with ever greater precision. This helps cut through the chronological fog of the Younger Dryas, allowing for correlations between events across the globe. Even from orbit, satellites contribute through gravity mapping. By measuring minute variations in Earth's gravitational field, these missions can detect density anomalies beneath ice sheets or oceans, helping to locate potential impact craters like the one under the Hiawatha Glacier or identify other hidden basins that might hold clues. This technological arms race is turning speculation into data. Each new instrument provides a finer lens, a sharper scalpel to dissect the past. It allows hypotheses to be tested with a rigor that was impossible just a generation ago. For every claim of nanodiamonds, there is now a machine to analyze their crystal structure and origin. For every theory about firestorms, there is a method to quantify the soot and trace its chemical signature. This makes the present moment uniquely exciting for this mystery. We are no longer reliant solely on what is visible on the surface or painfully unearthed by trowel. We can now see through forests, read the chemistry of a pinch of dirt, and sense the shape of things hidden under miles of ice. The coming years promise a flood of new data, each discovery potentially tipping the scales in the great debate. The story of our deep past is being rewritten, not just with new ideas, but with new ways of seeing, bringing us closer than ever to answering the ultimate question of what truly happened when the world grew cold. There is a primal power to the story of a world remade in fire and ice. This narrative, where a single day from the cosmos rewrites the destiny of species and civilizations, strikes a chord far deeper than a slow, incremental change in climate ever could. It speaks to something ancient within us, a recognition that history is not always a smooth river, but can be a waterfall where the flow of time is shattered by a single, decisive event. This psychological draw is known as catastrophism, and it stands in stark contrast to the gradualism that has long been the bedrock of conventional geology and archaeology. Gradualism tells a patient story, one where mountains rise grain by grain over eons, and cultures evolve through countless small adaptations. It is the story of a planet that changes at a pace almost too slow to notice. Catastrophism, on the other hand, is the story of the lightning bolt, the earthquake, the flood. It is history written in exclamation points. Our myths and legends are saturated with this archetype. From the lost continent of Atlantis sinking beneath the waves to the great flood narratives found on every inhabited continent, humanity has repeatedly told itself stories of a golden age brought to a sudden, dramatic end. These are not just tales, they are cultural memories packaged as metaphor, speaking to our deep-seated anxiety about the fragility of our own world. Apocalyptic prophecies, whether religious or secular, tap into this same vein, a fascination with the idea of a clean slate, a dramatic purge followed by a rebirth. The Younger Dryas impact theory fits perfectly into this powerful narrative template. It is not merely a scientific hypothesis, it is a modern echo of those ancient stories, offering a tangible, evidence-based explanation for a primordial reset. It transforms myth into potential history, giving a specific date and a physical cause to the archetypal fall from grace. This is a large part of its immense appeal. It satisfies a deep human craving for a story that is both epic and explanatory, where the heroes and victims are our own ancestors, and the villain is a piece of the universe itself. This inherent appeal, however, carries a significant risk. The very power of the story can sometimes outshine the rigor of the evidence. Passionate belief can lead to seeing patterns where none exist, or interpreting ambiguous data through the lens of a preferred narrative. This is the cautionary note from the scientific mainstream, a reminder that a compelling tale is not the same as a proven fact. The history of science is littered with beautiful, captivating ideas that ultimately collapsed under the weight of contradictory data. Yet, there is a crucial counterpoint to this caution. Nearly every paradigm-shifting truth in human history began as a heretical idea, ridiculed and opposed by the established order. The notion that continents drift, that microscopic germs cause disease, or that the universe is expanding were all once considered catastrophic to the prevailing worldview, in both senses of the word. Skepticism is essential, but so is the intellectual courage to entertain a radical possibility when the old models fail to explain all the clues. This meta-reflection helps us understand the intense, often polarized debates surrounding the Younger Dryas impact theory. The passion it generates is about more than platinum spikes and nanodiamonds. It is a clash between two fundamental ways of seeing history, one patient and incremental, the other sudden and revolutionary. It is a debate about the very rhythm of time. For supporters, the theory represents a necessary correction, a willingness to accept that our planet's story includes dramatic, unpredictable chapters. For skeptics, it represents a seductive but potentially simplistic shortcut, a retreat from the complex, gradualist explanations that have so successfully unraveled other deep time mysteries. Recognizing this psychological and philosophical dimension adds a rich layer of understanding to the entire investigation. It reminds us that science is not a cold, purely mechanical process, but a deeply human endeavor, shaped by our innate love for a good story, our fear of catastrophe, and our enduring hope to uncover the true. No matter how startling, shape of our past, the stories we tell are not always fiction. In fact, some of humanity's oldest oral traditions demonstrate a startling capacity to carry precise environmental memory across staggering spans of time. Aboriginal Australian cultures, for instance, preserve detailed narratives of coastal flooding that describe shorelines from over 10,000 years ago, accurately matching the known geography from the end of the last ice age. These are not vague legends, but specific accounts of islands that were once hills and bays that were once plains, maintained through countless generations without a single written word. This proven longevity of oral history forces a profound reconsideration of other ancient tales. If sea level changes can be remembered for 10, could the visceral trauma of a sky filled with fire and a sudden, crushing cold also have been transmitted? The detailed descriptions found in global mythologies of celestial battles, raining stones, and a long darkness begin to look less like imaginative allegory and more like potential eyewitness reports. Filtered through time and symbol, but rooted in a shared, horrific experience, this line of inquiry reveals the sophisticated mechanism of myth-making. Catastrophic real-world events do not enter oral tradition as dry historical records. They are encoded. The terrifying comet becomes a fiery dragon or a wrathful god. The impact winter becomes a long night sent as punishment. The floods from melting ice become a great deluge unleashed by the heavens. The literal truth transforms into symbolic narrative, a form that is more durable, more teachable, and more meaningful to a culture trying to explain why their world changed. This process is not a corruption of fact, but its preservation in a cultural capsule designed to survive. It blurs the line we often draw between science and the humanities, suggesting that indigenous knowledge systems are not merely spiritual traditions, but can be repositories of empirical data. They offer a unique window into the past, one that records human perception and environmental consequence in a way that ice cores and soil layers cannot. When a story describes the sea rising to drown a sacred mountain, it provides a geographical marker and an emotional timestamp. When a saga tells of a time when the sun hid and the game disappeared, it records ecological collapse and societal stress. These narratives become complementary evidence, a qualitative human record to set beside the quantitative data of platinum spikes and temperature proxies. They ask us to listen to the oldest stories not as fairy tales, but as the testimonies of survivors, carefully packaged and passed down through the ages. This perspective does not demand we take every myth literally, but it insists we take them seriously. It proposes that within the symbolic language of gods and monsters, there might be encrypted observations from the edge of extinction, waiting for us to learn how to decode them. Beyond the established realms of geology and astronomy, the Younger Dryas mystery has also sparked frameworks that challenge our most fundamental assumptions about the cosmos. One of the most unconventional is known as the electric universe theory. This perspective views the cosmos not through gravity alone, but as a dynamic electrical system, where planets and stars are connected by vast currents of plasma. From this vantage point, the event 12,800 years ago was not merely a kinetic impact from a chunk of ice and rock. Proponents suggest it was an electrified encounter, a moment when Earth moved through a dense filament of this cosmic plasma, or came perilously close to a charged celestial body. In this scenario, the primary destructive force would not have been just impact and fire, but immense arcs of electrical discharge leaping between the comet and our planet's surface. These arcs, theorized to be of planetary scale, would have acted like cosmic lightning bolts of unimaginable power. The theory proposes that such discharges could instantly fuse rock and soil into glass, carve out vast geological features with a single stroke, and explain the global layer of melted and nanodiamonds through electrical transmutation rather than sheer impact pressure. It offers an alternative explanation for enigmatic landforms like the Carolina Bays, interpreting their uniform alignment and raised rims as scars from a torrent of plasma blasts sweeping across the landscape. Rather than from wind or oblique impacts, this framework is not accepted by mainstream science, which finds its underlying plasma cosmology at odds with well-tested astrophysical models. Yet its very existence is telling. The fact that the Younger Dryas evidence is robust enough, yet mysterious enough, to inspire such radically different interpretations speaks volumes about the puzzle at hand. It shows that the standard models of comets and craters, while powerful, do not yet answer every question to everyone's satisfaction. The electric universe theory, and others like it, represent the far edges of speculation, where unanswered questions fuel creative and often controversial thinking. They remind us that profound mysteries have a unique power to push the boundaries of inquiry, inviting us to question not just what happened, but how the very forces of nature might operate in ways we have yet to fully comprehend. This diversity of thought, from the rigorously peer-reviewed to the boldly heterodox, ensures the investigation remains vibrantly alive. It underscores a crucial point. The final chapter on the Younger Dryas is far from written, and the search for answers continues to reshape our understanding of both Earth's past and the dynamic system we call home. Even catastrophe can plant the seeds of something new. In the ashes of a shattered world, the most profound human revolution may have quietly taken root. The traditional story of agriculture begins in the Fertile Crescent around 9,500 years ago, a seemingly spontaneous bloom of cultivation that gave rise to cities and empires. But what if that bloom was not spontaneous at all? What if it was a hard-won adaptation, born from the desperate need to survive a 1,000-year winter? Some researchers propose a startling link, suggesting the very climate chaos of the Younger Dryas served as the crucible for farming. With megafauna populations collapsing and familiar hunting grounds transformed, the old ways of life were becoming untenable. Communities faced a stark choice: adapt or face increasing hardship. In this pressured environment, the slow, deliberate process of plant domestication may have shifted from a casual experiment to a vital strategy. The erratic climate itself could have acted as a selective force. As certain wild grasses like emmer wheat and barley struggled in the cooler, drier conditions, their hardier mutants, those with seeds that clung to the stalk rather than scattering to the wind, would have been more easily gathered by human foragers. Unknowingly, these early people began selecting for the very traits that make crops reliable. They were not inventing agriculture from scratch so much as partnering with resilient plants in a changing world. The timeline is provocatively aligned. The Younger Dryas cold snap ended abruptly around 11,600 years ago. Within just a few centuries, the first definitive evidence of cultivated cereals appears in the archaeological record of the Levant. Sites like Tell show this transition in layers of soil, where the bones of gazelle and other game give way to grinding stones and the carbonized remains of domesticated rye. This was not an overnight switch, but a gradual reorientation of an entire society's relationship with nature, likely accelerated by environmental necessity. The monumental project of, built during this very period of climatic stress, adds another layer. To feed the large gatherings of people required to erect such stones, some archaeologists theorize that organized cultivation of wild grains may have been necessary, a form of proto-farming to support ritual and community. This suggests the birth of agriculture was not merely a practical response to hunger, but may have been intertwined with a spiritual and social response to catastrophe. An effort to create order and ensure abundance in a world that had proven frighteningly unstable. Thus, the comet's legacy becomes deeply paradoxical. The same event that may have erased certain paths of human development forcefully opened another. It channels the narrative away from pure loss and toward a theme of resilient innovation. From the chaos of fire and ice emerge the patience to sow a seed and wait for harvest, transforming humanity from followers of the herd to shapers of the landscape. This connection reframes one of our greatest leaps not as a sudden spark of genius, but as a slow, stubborn answer to a world remade. A testament to the human capacity to find new ways to live when the old ones vanish. The silent ruins we seek may lie beneath the waves. To follow the trail of lost Ice Age societies, science must now dive into the planet's most challenging frontier, the submerged continental shelves. This is the domain of submerged prehistoric archaeology, a field that merges the meticulous work of the dig site with the advanced technology of deep-sea exploration. Its mission is to map the drowned landscapes where ancient coastlines once thrived, hunting for the settlements that vanished when the seas rose. The challenge is immense. Water obscures, erodes, and buries evidence under layers of sediment. Yet, with each technological leap, this watery frontier yields more tantalizing clues. In the Gulf off the west coast of India, sonar surveys have revealed what some researchers interpret as large, geometric structures and artifacts, including worked wood and stone tools. Recovered from depths that were dry land over 9,000 years ago. While the findings are hotly debated, they highlight the potential of these unexplored zones. Similarly, in the cold, dark waters of the Baltic Sea, divers and robotic submersibles have documented astonishingly well-preserved sites, such as a 9,000-year-old stationary fishing trap constructed from woven branches, a snapshot of daily life from a shoreline that no longer exists. These projects rely on tools far removed from the traditional archaeologist's trowel. Autonomous underwater vehicles, or UVs, glide over the like robotic eyes, mapping vast areas with sonar and high-definition cameras. When a promising anomaly is detected, remotely operated vehicles, or ROVs, descend, equipped with robotic arms to carefully retrieve artifacts or take core samples from the sediment. These sediment cores are like time capsules pulled from the seabed, containing pollen, charcoal, and even microscopic evidence of human activity, such as the fragments of burnt bone or distinctive algae that flourish near human habitation. Each core sample is a piece of a gigantic global jigsaw puzzle. The difficulty of working at depth, with limited visibility and tremendous pressure, makes every discovery hard-won and extraordinarily precious. But the potential reward justifies the immense effort. A single confirmed settlement on an ancient shoreline, dated to the period just before the rapid sea level rise, would provide direct, tangible evidence of the coastal societies the impact hypothesis suggests were lost. It would move the discussion from theory about population movements to proof of established communities. Furthermore, the state of such a site could tell a vivid story. Was it abandoned in an orderly fashion, suggesting a gradual retreat from rising waters, or does it show signs of a sudden inundation, with tools and hearths left as they were, potentially hinting at a catastrophic flood? This underwater search is where the comet impact theory could meet its most compelling evidence. If the event triggered not only fire and ice, but also the catastrophic melt pulses that rapidly raised ocean levels, then the ruins of its most vulnerable victims are not lost to time, but preserved in the cold, dark museum of the deep sea. Finding them would give a name and a place to the abstract idea of a lost ice age world, turning a global climate model into the story of a specific village that one day met the sea. Our own bodies may hold the oldest memories of all. Beyond the stones and the soil, a different kind of archive exists, written in the language of life itself. The study of ancient DNA allows scientists to read this biological ledger, tracing the lineage of our species back through thousands of generations. What these genetic timelines sometimes reveal are moments of profound crisis, points where the human family tree seems to narrow to a few fragile branches. These are called population bottlenecks, and one such constriction appears in the shadows of the Younger Dryas. The evidence is not found in a layer of charcoal, but in the patterns of our genes. When a population shrinks dramatically, the genetic diversity of the survivors becomes a kind of timestamp. Future generations inherit a less varied genetic palette, a signature of that ancient brush with extinction. Researchers can analyze the DNA of modern populations, and using sophisticated statistical models, work backward to estimate when these founder events occurred. For the ancestral populations that first entered the Americas, the genetic data points to a significant bottleneck right around 12,800 years ago. This suggests the group that would give rise to many Native American peoples was once very small, potentially isolated for a time before expanding into a new world. This biological clue operates independently of the archaeological debate. It does not tell us why the population shrank, only that it did. But when placed alongside the geological evidence of fire and ice, it creates a powerful synergy. A catastrophic event that devastates environments and food sources would inevitably put tremendous pressure on human groups, leading to population decline, fragmentation, and migration. The genetic bottleneck is the expected human echo of a planetary disaster. It translates the abstract concept of societal disruption into the intimate language of family and survival. It suggests that the story of the comet is not just about lost tools or extinct animals, but about us, about a time when the number of human beings on the entire continent may have dwindled perilously low. Our genomes, in a very real sense, could be carrying a scar from that long winter, a molecular memory of resilience passed down from the few who endured. This connection is profound, linking the vast, impersonal forces of the cosmos directly to the biological legacy of every individual descended from those survivors. It means the evidence for this ancient event is not just buried in the ground or locked in ice, it is alive within us. A silent testament written in every cell to a time when the human story almost turned a different page. The invisible world of the past is being rebuilt inside the most powerful computers on Earth. To move from a collection of clues to a full picture of catastrophe, scientists are constructing digital replicas of our planet's ancient atmosphere and subjecting them to the ultimate stress test. A simulated comet strike. These are not simple animations, but complex climate models, vast mathematical frameworks that calculate the physics of air, water, and energy on a global scale. Researchers begin by setting the stage, programming the model with the known conditions of the world 12,800 years ago, a world just emerging from an ice age. Then they introduce the variable, a virtual comet. They can adjust its size from a few hundred meters to several kilometers across. They can change its composition, whether it is a fragile ball of ice or a denser rocky asteroid. They can alter its entry angle, determining whether it plunges steeply or skims the atmosphere to fragment. With each adjustment, they run the simulation, unleashing a digital apocalypse to see what unfolds. The results are both terrifying and illuminating. A common outcome from a large, fragmenting airburst shows a rapid, dramatic injection of dust and soot into the upper atmosphere. The supercomputer calculates how these particles spread, carried by global wind patterns, until they form a thin, sun-blocking veil around the entire planet. The model then reveals the consequence: a sharp, sustained drop in surface temperatures. The numbers that flash onto the screen align eerily with the data pulled from real-world proxies, like the oxygen isotopes in Greenland ice cores that tell us how cold it got. The simulation can show how this cooling would not be uniform, but would disrupt the planet's weather engines. It predicts shifts in precipitation belts, turning some regions drier and others wetter, patterns that match evidence of droughts and changing lake levels found in the geological record from that time. Perhaps most critically, these models can simulate the proposed knockout blow to the Atlantic circulation. The virtual comet strike, combined with the meltwater from destabilized ice sheets, pours a massive pulse into the North Atlantic. The supercomputer calculates how this lighter caps the denser, stifling the sinking process that drives the Great Conveyor Belt. The model's animation of this current slowing to a crawl, and the subsequent plunge in temperatures across the northern hemisphere, provides a dynamic visual for a process we have only inferred from static clues. This is the power of simulation. It turns a list of effects into a coherent, visual story of cause and chain reaction. Each run is a question posed to the past, and the answer is a climate snapshot we can compare, point by point, with the one preserved in ice and sediment. The closer the match, the more plausible the scenario becomes, transforming a captivating historical mystery into a rigorous digital experiment in planetary science. A compelling scientific hypothesis rarely stays confined to academic journals. The idea of a world-altering comet impact has ignited the public imagination, finding its way into best-selling books and high-budget documentaries. Often under dramatic titles that promise to reveal ancient apocalypses, this media spotlight creates a powerful, yet precarious, bridge between the laboratory and the living room. On one hand, it generates widespread fascination, drawing essential public interest and, indirectly, the potential for research funding. A captivating documentary, can inspire a new generation of geologists and archaeologists. On the other, the drive for compelling television can sometimes stretch thin evidence into certainties, favoring narrative punch over procedural caution. The line between responsible science communication and sensationalism becomes blurred when complex, debated data is presented as a solved mystery. With ominous music and CGI fireballs overshadowing the careful language of peer review, this tension is inherent in sharing any profound discovery. The human mind is wired for story, for clear villains and decisive events, not for statistical probabilities and ongoing scholarly debate. Media producers know this, and the most memorable titles often lean into catastrophe. Yet this very dramatization can backfire within the scientific community, causing some researchers to distance themselves from a theory they feel has been misrepresented, potentially stifling open discussion and marginalizing legitimate work. The public perception shaped by this media landscape becomes its own force. It determines which theories feel true in the cultural gut, influencing which documentaries get sequels, which books top charts, and ultimately, which avenues of inquiry seem worthy of pursuit. This reminds us that the journey of a radical idea is never purely about evidence. It is also a story of how that evidence is communicated, who gets to tell it, and what version of the past we are collectively ready to hear. The search for lost worlds is never just about the past. It is about the people connected to that past in the present. As this theory reaches into the most remote and sacred corners of the globe, from submerged coastlines to ancient ceremonial mounds, it inevitably touches the lands and living traditions of indigenous peoples. Their ancestral territories often hold the very clues researchers seek, and their oral histories carry echoes of the events we try to scientifically model. This intersection creates a critical ethical responsibility, one that goes far beyond securing a digging permit. Too often in history, the pursuit of knowledge has followed a familiar, painful pattern. External researchers arrive with exciting theories, treat local communities as mere sources of data or labor, extract artifacts and stories, and then depart, leaving little behind but disruption. Oral traditions are mined for details that seem to support a scientific hypothesis, while their deeper cultural meaning and ownership are disregarded. This is a form of intellectual extraction, where indigenous knowledge is taken to fuel an academic narrative without genuine partnership or return. The excitement over a potential paradigm-shifting discovery can sometimes overshadow the living people for whom these sites are not a mystery to be solved, but a sacred heritage to be stewarded. A responsible investigation today must actively work to avoid repeating these colonial patterns. It requires a fundamental shift from seeing communities as obstacles or sources, to recognizing them as essential partners and rightful authorities. This means collaborative approaches built on mutual respect and consent, where research questions are developed together, where indigenous scholars and knowledge keepers lead the interpretation of findings, and where any benefits from the work, from educational opportunities to control over cultural materials, are shared. It means listening to oral histories not as crude data points to be validated by science, but as sophisticated, sovereign ways of knowing that offer a different, equally vital dimension to the story. After all, who better to help interpret the meaning of an ancient site than the descendants of the people who may have built it? This ethical framework transforms the quest. It is no longer just about what we can uncover from the ground, but about how we uncover it and for whom. The goal becomes not merely proving a comet struck, but weaving a more complete and respectful tapestry of the human experience, one that honors both the rigor of the laboratory and the wisdom of the land. This approach ensures the search for lost civilizations enriches our shared understanding, without creating new losses in the process. Behind every groundbreaking discovery lies a more mundane reality, the question of funding. These grand searches across continents and under ice sheets are not just intellectual pursuits, they are massive logistical undertakings with staggering price tags. Who decides to pay for a drill rig on a remote glacier, or a fleet of underwater robots scanning a drowned coastline? The answer reveals a hidden ecosystem of support that ultimately shapes what mysteries we can solve. At the highest level, national science foundations are the traditional pillars. Agencies like the National Science Foundation in the United States or the European Research Council fund fundamental research, often through a fiercely competitive grant process. Scientists must submit detailed proposals, laying out their hypothesis, methodology, and expected outcomes, which are then scrutinized by panels of peers. This system prioritizes rigorous, testable science, but it can be challenging for highly speculative or interdisciplinary ideas that don't fit neatly into established academic boxes. A theory that bridges geology, archaeology, and climatology might fall between the cracks, deemed too archaeological for a geology panel or too geological for an archaeology fund. This is where private philanthropy and visionary donors often step into the gap. Wealthy individuals fascinated by history's big questions can provide the crucial seed money for exploratory phases. Funding initial field surveys or the development of new dating techniques that larger agencies might deem too risky. These private grants offer flexibility and speed, allowing researchers to follow a promising lead without years of bureaucratic delay. For particularly dramatic and public-facing projects, crowdfunding has emerged as a modern tool. Imagine a campaign to fund the crucial drilling into the Hiawatha crater ice, directly inviting the global public to become patrons of this deep-time detective story. A few dollars from thousands of enthusiasts can collectively finance a core sample, making the audience literal stakeholders in the quest. Yet this landscape is also a battlefield of credibility and controversy. A theory challenging established paradigms can face an uphill battle for traditional funding. Reviewers invested in existing models may be skeptical, viewing the evidence as insufficient or the conclusions as too extraordinary. This creates a catch-22. Without significant funding, you cannot gather the definitive evidence, but without definitive evidence, you struggle to get the funding. The pursuit of knowledge, therefore, is filtered through a lens of economic and social priorities. It asks what stories about our past we, as a society, deem important enough to invest in. Does understanding a potential global catastrophe rank above other scientific inquiries? Does the mystery of lost cultures capture the public imagination sufficiently to open wallets? This reality directly shapes the pace of discovery. A well-funded team can analyze hundreds of soil samples with the latest spectrometry, while a rival idea might languish for lack of resources to test a single crucial site. The map of our ancient past is not drawn solely by evidence, but by the resources available to search for it, reminding us that every clue pulled from the earth is also a product of the very modern world that seeks to understand it. The final answer is not yet written in stone or ice. Right now, across the globe, a handful of critical experiments are, each with the potential to tilt the scales in this great debate. The most anticipated result lies in Greenland. Teams are meticulously working to extract and date the rocks from beneath the Hiawatha Glacier. A confirmed age of 12,800 years for that colossal crater would be the single most transformative piece of evidence, a ground zero that ties every other clue together. Simultaneously, oceanographers are guiding robotic arms into the deep, pulling up sediment cores from the submerged plains of and. Within those muddy cylinders, they search for more than ancient pollen or animal bones. They hunt for the subtle chemical signature of human presence, charcoal from campfires or microscopic flakes of worked stone. That could prove these lost landscapes were indeed inhabited heartlands before the seas rose. Above us, the watch continues. New satellite missions, equipped with infrared telescopes far more sensitive than their predecessors, are joining the silent vigil, scanning the darkness to catalog every sizable object that crosses Earth's orbital path. This isn't just about future safety, it's about understanding the past. By mapping the population of near-Earth objects, especially within streams like the, astronomers can better model the likelihood and potential effects of a fragmented comet encounter, providing a statistical backbone to the ancient hypothesis. The coming 5 years promise a flood of new data from these fronts, so where will the theory stand when it arrives? It could follow several paths. If the crater dating and cores deliver compelling confirmation, the idea may shift from a controversial hypothesis to a fundamental chapter in earth science textbooks, reshaping our understanding of the Holocene's rocky start. It could also settle into a nuanced middle ground, accepted as a real climatic event that contributed to extinctions and cultural shifts, but not the sole, dramatic cause of every mystery. Or if the key evidence fails to materialize or is contradicted by new findings, the theory may recede, remaining a fascinating but unproven possibility for a small group of researchers. This uncertainty is not a flaw, it is the thrilling essence of science in motion. We are not looking back at a settled story, but peering over the shoulders of those who are actively writing it. The next core sample, the next radar scan, the next orbital calculation could be the one that changes everything. This means you and I are not passive audiences to a finished tale. We are witnesses to a live investigation, one that connects the deepest past to the immediate future. To follow this story is to participate in a grand, real-time puzzle, a reminder that history is not just what happened, but what we are still in the process of discovering. This is a story that reaches beyond textbooks and into the very bones of our shared memory. If the sky truly fell 12,800 years ago, it forces a quiet, personal kind of reckoning. It asks us to reconsider our own place in a cosmos that is not a passive backdrop, but an active participant in our history. Our ancestors were not just shaped by slow rivers and changing seasons, but potentially by a single, brilliant, terrifying moment from the depths of space. That realization carries a profound duality, a lesson in both fragility and astonishing strength. On one hand, it underscores our vulnerability. It shows that all human achievement, every tool crafted, every story told, every community built, exists on a foundation that can be shaken by forces entirely beyond our control. The most sophisticated culture of its time could be brought to a crossroads by a visitor from the solar system's distant past. This isn't a cause for fear, but for a deep humility, a recognition that our destiny is woven into a much larger tapestry of cosmic events. Yet, the very same evidence speaks overwhelmingly to resilience. The story does not end with the impact, it continues with the survivors. It continues with the hands that carved the pillars of, with the generations that learned to nurture wild grasses into wheat, with the voices that passed down the warning in a flood myth. The comet may have provided a brutal catalyst, but the response was utterly human, a testament to an indomitable will to make meaning, to rebuild, and to remember. Try, for a moment, to stand in their world. not as a scientist analyzing data, but as a person waking to a sky on fire, to a winter that refused to end. The lived experience of those generations is almost beyond our comprehension, a slow-motion unraveling of everything they knew. What stories did they tell their children to explain the long cold? What ceremonies did they create to plead for the sun's return? The monuments they left behind and the myths we inherited are likely their answer, the emotional and spiritual artifacts of that trauma. They are not just records of an event, but records of a people choosing to face the unimaginable and forge a new path forward. So, what if this theory is true? It means our oldest stories might be more than metaphor, they might be heirlooms of survival. It means the dawn of civilization as we know it might have been a second dawn, a rebirth from the ashes of a forgotten world. Most importantly, it connects us directly to that ancient struggle. It suggests that the curiosity driving us to solve this mystery today is the same spark that compelled our ancestors to look at a sky and a frozen land and decide to build something new. That spark, it seems, is the one thing a comet could not extinguish. The journey ends not with a single answer, but with a transformed question. We have traced a line from the chemistry of a dust layer to the psychology of a myth, from the silence in an archaeological stratum to the roar of a simulated airburst. This is the true power of the comet impact hypothesis. It does not simply propose an event, it builds an entire world of interconnected evidence, a tapestry woven from geology, climatology, archaeology, and even the study of stories. In doing so, it performs a vital service for our understanding of history. It reminds us that the past is not a flat timeline, but a deep, complex system where a single spark in the heavens can ignite a chain reaction that echoes for. The fierce debate surrounding it is not a sign of weakness, but of health, a rigorous conversation that forces every piece of the puzzle to earn its place. Whether the final verdict leans toward confirmation or a more nuanced explanation, the investigation has already succeeded. It has shattered the old, comfortable assumption that human prehistory was a slow, predictable climb. In its place, it offers a more dynamic and humbling vision, one where progress is not guaranteed, where civilizations can be interrupted, and where the sky itself is a character in our story. This perspective reframes our own moment in time. We live on a planet that orbits through a solar system still rich with wandering debris, and within a climate system that our own actions are now influencing. The ancient story, if true, becomes a case study from the deep past, a lesson in planetary interdependence and resilience. It asks us to look at our own global challenges, from asteroid defense to environmental stewardship, with the long view of history in mind. The curiosity that drives us to solve this 12,000-year-old mystery is the same force that can guide us toward a more secure future. It is the desire to understand the forces that shape worlds so that we might better shape our own. If this exploration of lost ice and forgotten fire has sparked your imagination, there are countless more historical puzzles waiting to be unraveled. Consider subscribing to continue the journey into the shadows of our past. And we would genuinely love to hear your perspective down in the comments. After following the evidence across continents and through time, where does your curiosity land on this monumental question?